So now I'm going to talk a little bit more about this rank size rule that I did in a different video for regression analysis. We had seen that a different sample size, different number of cities gave us different coefficients. So I'm going to play around in R and show a little bit of some of the things that R can do. I'm also going to talk a little bit about how the numbers work, specifically with logs and exponents, right? So one thing to think about is that if I have a ranking of like largest to smallest for New York on down, it's be the same ranking whether it's in population or log population. Right? It's called a monotonic transformation. Changing the number does not actually change the ordering of the numbers. So when I do this ranking, the rank of the log is going to be the same as the rank of the regular population. Right? We can actually see that. One thing we can do is we can look at the order. Actually, we can sort data 2 by order. I'm going to replace data 2 with this rank ordering, and we can see here that we go from the first rank. So remember, the log of 1 is 0. So this is New York, which is the first rank, and then the rank increases as the size decreases. Right? These are both in logs. If we take the correlation, and I do a Spearman correlation, which is non-parametric, you can actually see the correlation is -1, and that means that simply in terms of rank order, which the Spearman uses, it's going to be a perfect correlation because the rankings are exactly in opposite directions, right? So data 2 is now ranked from low to high. We use the order function, right, in terms of rank, and then we see how that worked. All right, so now what I'm going to do is I'm going to take a loop, all right, and I'm going to increase sample size. I'm going to start with 25 because you can't have a regression with too few observations, and then I'm going to have the max depending on the time it takes and the computing power. All right, one thing I'm going to do right now is I'm actually going to start my loop. All right, and then I'll talk about it as I go. One thing I put in here is I actually print as I go the percentage that is done. So the max is the rows I have, which is 15,000. But again, I could pull in my original data with even more observations, and then this is going to change the number only once. All right, and so I've got the max showing up a couple times, but I don't have to change 15,000 to 30,000 more than once. Right, so this takes the number of rows and does the max. Right? And so I'm going to start this, and as I go, I'm going to talk about it. So this is actually 1% done, and it's going to go as I talk. Right, so you can see the computing power. Your computer might be a little faster. All right, so the thing you do with a table, I'm going to make a table and I'm going to make a graph, is when you make a table, you start with null, so that the first item in the loop as it runs is going to attach to something you've already made. If you don't have something to attach to, it won't run. So I make a null table called reg table, and I'm going to attach one by one as I run it through the loop. Right? I also have the size because that's going to be one of my columns, right? And when I plot, so that's also null. And so as it goes, it's going to attach to that every time. So for I in 25 to max, so it's going to start at 25, 26, 27, all the way to the number of rows, which is 15,147. It's going to do the following. Right? First, I make a new data thing called data 2. I don't overwrite it. Right? It's going to pull from data 2, and it's going to say which of these has a rank of size less than I. Right? So it's every I starting at 25. It's going to say data 2 is only the rows where the rank is 25 or less. Right? Then it's going to go through and do 26 and so forth. Right? So for that, which has a size of 25 the first time, I'm already 78% done. I'm going to do a regression, and so that is going to be rank on size, and it's going to say the data set is the data 4 I just made. Right? Now I'm going to make a couple things. I'm going to make a vector. The first item is going to be 25. That's going to be my size, and then every time it's going to make an additional row. It's going to take size and it's going to add I to it. All right, and I don't actually think I need size 1 for that. I think I can just add to it every time. So this might be superfluous. Right? Sometimes you actually need something to add to it, but right now I'm going to say take and add I every time. So it'll be first 25, then 26, all the way to 15,000. Right? The table is going to have multiple rows. It's going to take the original table first. It's null. Right? It's going to take the 25 for it, and then in the regression, it's going to make the coefficients. So it's just going to pull. If you look reg coefficients, it's just the numbers here. So it's going to take the table and it's going to add the coefficients below it. Right? So again, I'm going to make a vector called size, and I'm going to make a table that gives me all the regression coefficients. Right? And that's going to start at 25, 26, and it's already looped through. Right? Reg table is it's going to basically take my table that I made and the size I made and combine them. Right? And so it's going to have a nice column of observation sizes to it. So if I look at head reg table, right? It's going to start at 25 and go up, and it's got the intercept and it's got the beta coefficient on that. You can actually see the intercept is falling too, but look at size, it's 0.384, and it starts to rise, and then it's going to fall over here, right? And so I gave the table nice rows, and you can see intercept and ln size, right? And then the tail we can run as well as we did the head, right? You can see here that the size has gone down to negative 0.8, and that's over here. And then I did a plot, right? And so this is already plotted, and so we're going to plot reg table columns 1 and 3, which is the number of observations here. We're skipping the intercept, only doing the slope. We're doing it as a line graph, type L, width of 2. The X label is sample size, Y label is beta of ln size, and this is what we get, right? You can see here that it's very far from 1. There's a little bit of a dip, rises again, and then overall it gets closer and closer and closer to 1. Maybe if we had 30,000, maybe if we started with our original data from before, we actually would get to 1. But as this stands, even for the largest cities, the coefficient isn't 1, as the theory predicts, right? So that's what the loop did, right? So again, I was able to plot all the way from 25 to the size of the sample. I got different coefficients. I take the coefficients, I make a table, right? And so this coefficient has all, 15,000 coefficient estimates, and then I just pull out the coefficients I want, and then I'm able to plot them as a relationship between the sample size and the beta that I collect. So that's what I did. Now I could redo it with the larger data set, and I could only change one number and rerun as long as I'm pulling from the same data set name. Right, but this shows the relationship that perhaps given enough cities it would approach 1, but with only the 15,000 with a population of 1,000 or more, this law doesn't hold. Right, so we're able to run a loop, to run multiple iterations of a regression, and then compare them, and then present them visually.